Good evening, all. We will wait for some more time so that some more people will join. Are you able to see my slides?
Yes,
Okay. Around 6:05 we can start. Can we start? Hello.
yes, ma'am.
Hmm. Good evening, all. Welcome back to NPTEL PMRF tutorials on Introductory Organic Chemistry 2. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. Last week, we have discussed about assignment questions regarding enols and enolates. This week also, we will continue on the same topic, enols and enolates, along with Aldol condensation reaction. So, we will be discussing previous year questions of assignments from week 6 today. So, going to first question. This is the question number 1. For the sequence of reactions shown below, they have given a alpha bromoester and treated with zinc to get a compound A. Then they treated it with benzaldehyde and water to get compound B. And here they have given some options like compound A is a lithium enolate. The second step is the benzylic acid rearrangement. Compound B has two aromatic rings. Compound A has two aromatic rings. So we have to find which is the right statement among these four statements. Okay. So do you have any idea regarding what is this name reaction that is taking place here? Any idea? So this is a Reformatsky reaction as it is involving a alpha halo ester and a zinc, and then condensation is taking place in the presence of an aldehyde. So the Reformatsky reaction is an organic reaction which condenses aldehydes or ketones with alpha haloesters using metallic zinc to form beta hydroxy esters. So this is the definition of Reformatsky reaction. So this is the mechanism involving. So in the presence of zinc, the alpha halo ester will undergo an arrow pushing mechanism like this. The zinc will add electrons to this oxygen. Then this carbon oxygen double bond will break. This electron density will shift in this direction, and this bromide will get eliminated. Then it will result in the formation of a zinc enolate. Zinc enolate is also similar to an enolate. Then it will undergo reaction similar to enolate. It will add on to this aldehyde like this. So this is the zinc enolate we are having. So this zinc oxygen bond will break. Then this double bond, carbon carbon double bond will go and attack on this aldehyde, and it will abstract the zinc bromide. So we will get a transition state like this, and upon workup we will get beta keto ester. So everyone clear regarding the mechanism of Reformatsky reaction? Hello?
Yes, ma'am.
Okay. So we will see what is happening in the question that is given to us. So we are having this alpha bromo ester. So it upon treating with zinc, the zinc will add on to this oxygen. Then this carbon oxygen double bond will break, and this electron density will shift, resulting in the formation of a double bond here. And this CBr bond will break, eliminating bromide ion. So we will get this species zinc. So this is compound A in our reaction. So compound A is not a lithium enolate, and compound A does not have two aromatic rings. So that two options can be ruled out here. Okay. Is that clear? Compound A is not a lithium enolate. It is not having all Li. It is having O, Z and Br. So it is a zinc enolate, not a lithium enolate. And it is having only one aromatic ring. So those two options can be ruled out. Then compound A, it can react with this benzaldehyde like this. It will form a six-member transition state like this. Then this oxygen zinc bond will break, forming double bond here. Then this carbon-carbon double bond will go and attack on this electrophilic benzaldehyde, and it will abstract the zinc, resulting in formation of this kind of intermediate. Then this intermediate, upon treating with water or upon doing workup, it will result in the formation of a beta hydroxy ester like this. Beta hydroxy ester because this hydroxy group is present at beta position. This is alpha position. This is the ester. This is alpha position. This is beta position. So this is called a beta hydroxy ester. So this is compound B. So here we can see the compound B is having two aromatic rings. Also, this second step, like addition of this benzaldehyde, it is similar to aldol condensation reaction. It is not benzylic acid rearrangement. So we can conclude that out of these four options, compound A is not a lithium enolate, and the second step is not a benzylic acid rearrangement. Second step is compound A is not a lithium enolate. Then second step is not a benzylic acid rearrangement. It is aldol condensation. So this is also not true. Then compound A has two aromatic rings. That statement is also wrong. So the correct statement is compound B has two aromatic rings. Compound B has two aromatic rings as we have seen in the mechanism here. Here compound A is having only one aromatic ring, and compound A is not a lithium enolate, and this is not benzylic acid rearrangement. It is aldol condensation kind of reaction. Is this clear? Is question 1
Yes,
clear to
ma'am.
everyone? Okay, now we will move to question 2. Coming to question 2, which of the following aldehydes will undergo a Cannizaro reaction? So they have given 3 aldehydes, and the fourth option is all of the above. So which of these aldehydes will undergo Cannizaro reaction? So what is a Cannizaro reaction? So a Cannizaro reaction is a chemical reaction that involves base-induced disproportionation of two molecules of a non-enolizable aldehyde. This is important. Non-enolizable aldehyde to yield a carboxylic acid and a primary alcohol. So it will undergo reaction with a base. A non-enolizable aldehyde will undergo reaction with a base to give carboxylic acid and a primary alcohol. So does anyone have any idea regarding what is a disproportionation reaction? What is a disproportionation reaction? You might have studied in 12th standard and all. This is a basic reaction. So, a disproportionation reaction is a reaction in which the same element is simultaneously oxidized and reduced. So, this is a redox neutral reaction. The same element is undergoing oxidation and reduction. So that kind of reaction is known as disproportionation reaction. So Cannizaro reaction is also a disproportionation reaction. Here a non-enolizable aldehyde will undergo um, reaction to give a carboxylic acid and a primary alcohol. So we will see the mechanism of Cannizaro reaction before going to discuss the answer of this question. So here we have an aldehyde and a base. Then the base, here the aldehyde is non-enolizable. So the base cannot abstract any proton from the aldehyde. So the base will undergo nucleophilic addition and we will get a hydrate anion like this. The base will undergo nucleophilic addition to this carboxyl, and then this electron density will be pulled in this fashion and we will get a hydrate anion like this. Then here we have an hydroxyl group. You can see here we are having a hydroxyl group. Then the base will abstract the proton from that hydroxyl group and we get a hydrate dianion like this. Is this clear? What is happening here? First, we have a non-enolizable aldehyde. Non-enolizable aldehyde means that aldehyde does not have any alpha hydrogen. Alpha hydrogen means the hydrogen that is present adjacent to the carboxyl carbon. So here there should be a carbon and hydrogen. Then it is called alpha hydrogen. So here the aldehyde is not having any alpha hydrogen in case of Cannizaro reaction. So the base cannot abstract any proton from the system. Instead, it will add on to this carboxyl group and we will get a hydrate anion. Here nucleophilic addition is taking place. We will get a hydrate anion. Then here the hydroxyl group is having a hydrogen atom. The base will abstract that hydrogen atom and it will result in the formation of a hydrate dianion. Is this clear? Then this
Clear, ma'am.
okay. Then this hydrate dianion, it will undergo addition with this aldehyde. So the hydrate dianion, here the oxygen will push electron density like this and this hydrate will add on to the aldehyde. Here the hydrate will add on to this aldehyde. So what is happening? Here this will result, here the hydride is going and we are getting R double bond O minus. That is a carboxylate anion is forming and then we are getting, here the hydrate is adding and we are getting this molecule which will convert into an alcohol. So we in turn we are getting a carboxylate acid and an alcohol. So the aldehyde we are having, it is undergoing reduction to form an alcohol and it is undergoing oxidation to form an carboxylate anion. That is why we are calling this as disproportionation reaction. The same molecule, that is this aldehyde, it is undergoing an oxidation reaction as well as reduction reaction. So this is a disproportionation reaction and this is what is happening in a Cannizaro reaction. Is this clear mechanism?
Yes, ma'am.
Okay. So here they have asked which of the following aldehydes will undergo a Cannizaro reaction. So for a Cannizaro reaction, we have seen that the essential criteria is non-enolizable aldehyde. The aldehyde should not have any alpha hydrogen. So in case of formaldehyde, It is not having any alpha hydrogen, so it can undergo Cannizaro reaction. And in case of benzaldehyde as well, there is no alpha hydrogen, so it can also undergo Cannizaro reaction. And here, this tertiary butyl aldehyde, here it is also not having any alpha hydrogen. We can see its structure, double bond O H, and it is having three methyl groups. So here there is no hydrogen, methyl groups. So in case of this tert butyl aldehyde as well, it is not having any alpha hydrogen. So this is also possible candidate for Cannizaro reaction. So all the above three aldehydes can undergo Cannizaro reaction. Is this clear? Why we have chosen all these three aldehydes can undergo Cannizaro reaction? Because none of these aldehydes are having a alpha hydrogen that will enolize. Okay, is this clear?
Yes, ma'am.
Okay, we will go to question number 3 now. This is also a similar Cannizaro reaction. So in the reaction, the products X and Y are respectively. So here they have given two aldehydes and they have treated with a base. Then it will give a compounds X and Y. So we have to identify what is X and what is Y. So anyone have any idea? Like if I mark this as option A, this as option B, this as option C, and this as option D, what will be the right answer? Any idea? What will be the right answer? This is also Cannizaro reaction. So we have discussed the mechanism for Cannizaro reaction in previous question, and we have seen that it is a disproportionation reaction where the so here there are two aldehydes. So this we cannot say like it is disproportionation reaction, but we are having two aldehydes. So one of the aldehyde will undergo oxidation and one of the aldehyde will undergo reduction. So what will be the possible option? A, B, C, or D? Any idea? Okay, we will see the mechanism for this reaction. So out of these two aldehydes, formaldehyde is most reactive. Here, since it is an electron donating group, the electrophilicity of this aldehyde will be less. So formaldehyde will be more reactive than this aldehyde. So formaldehyde will react with the base and it will give the species hydrate anion. Then this base will again abstract this proton and we will get a dianion like this. Then what will happen? The dianion will react with this aldehyde. So this electron density from this oxygen will fall down and the hydrate will go and add on to this aldehyde. So what we will get here? We will get a carboxylate anion from this formaldehyde, and this species will undergo reduction. The aldehyde will undergo reduction and we will get an alcohol. So is this mechanism clear? This is also Cannizaro reaction as we have seen. Here we have two aldehydes. So out of that two aldehydes, formaldehyde is the most reactive. So it will react with the base first and it will generate this dianion. Then this dianion can react with this other aldehyde where it will act as a hydrate donor for reduction reaction to take place. So this compound, this dianion will convert into a carboxylate anion, and this aldehyde will convert into an alcohol upon reduction. Is this mechanism clear? Any doubt?
Clear, ma'am.
Okay. So we can go back to our question. So this was the question. So out of these four, which is the right answer? As we have seen in the mechanism, the right answer is option A. The first aldehyde will undergo reduction and the second aldehyde will undergo oxidation to form an alcohol and a carboxylate respectively. Now we will move on to question 4. So here, identify the final product of the following Reformatsky reaction. So they have mentioned it is a Reformatsky reaction. So this zinc bromide species will undergo condensation with this benzaldehyde, and upon workup we will get one of these one of these three products, or it can be none of the above. So we will see what is the right answer by evaluating the mechanism of Reformatsky reaction in this reaction that is given to us. Okay. So coming to the mechanism, here this species, here as it is attached to zinc, here this will be having a partial negative charge and this zinc will be having a partial positive charge. So this partial negative charge, that is this carbon, will add on to this benzaldehyde and we will get a species like this. Okay. Now here we have an hydroxyl group and here we have an ester. So this hydroxyl group can add on to this ester. So this carbon oxygen double bond will break. Then once it is coming back, this OET moiety will eliminate as it is a good living group and we will get this species. Is this clear? So as we have seen in Reformatsky reaction, here this center is having a partial negative charge. It will add on to this benzaldehyde. Here this bond will shift here. Here it will generate O minus and upon workup it will generate OH. Then that can add on to this ester. This ester is like 1, 2, 3, 4, 5. 5 carbon, like it is 5 atom distant. It is in 5 atom distance. It can form a 5 membered stable species. So this hydroxyl will add on to this ester and this OET will eliminate. So we will get this species. This is the product for this Reformatsky reaction. Is the mechanism clear?
Clear, ma'am.
Okay. So out of these three, this is the right answer as we have seen in the mechanism. This is the right answer. So Reformatsky reaction is also similar to Grignard reaction. Here instead of MgBr we have ZnBr. Here this will be having partial negative charge and it can add on to electrophiles. It is also similar to Grignard reaction. Now coming to question number 5. What will be the major product of following alkylation reaction? Here they have given an imine and it is reacting with n-butyl lithium in dry THF. So it will generate an enolate and then it will add on to this alkyl bromide and we will get one among these four products. So we can see what is the mechanism that is taking place here. So here there is three possibilities. Here this butyl lithium can abstract this proton, it can abstract this proton, or it can abstract proton from this CH3. So it can generate an anion here upon abstracting proton from this, and it can generate an anion here upon abstracting proton from this, and it can generate an anion here upon abstracting a proton from this methyl group. So there are three possibilities. Out of these three, in these two cases, In case number 2 and case number 3, these can be stabilized because of this resonance. Here there is chance for resonance, so these two can be stabilized. Here there is no such chance for resonance stabilization. Here the negative charge will come on carbon, it will be destabilized. So this species is not stable, so this chance can be ruled out. So there are two chances: either proton can be abstracted from this carbon or from this carbon. If proton is abstracted from this carbon, then alkylation will take place and it will give this product. And once if anion is formed here, then alkylation can take place and it will give this product. So both are possible. Now we will see the options and we will see out of these two what is there in the option. So we can see that CH2R, that product is not given in the option, so we can select this as the major product upon alkylation reaction taking place in this species. Is this clear? There are two chances. This can also take place, this can also take place because of this stabilization of this anion by means of resonance. So upon alkylation it will give either this product or this product. So we have been given this product in the option, so this will be the right option. All these three options can be ruled out. Clear? Sorry. Uh, is this clear?
Clear, ma'am.
Okay. So the right option is option A. Now coming to question number 5. Here they are asking for what identify the major product of the following reaction. So first they have treated with LDA-THF. So it will lead to formation of a lithium enolate, and then they are treating with an alkyl halide. So here there are two halides, two positions given, one with iodine and one with chlorine. So we will see what is the product P we are getting out of this four. What is the product P we are getting? So first, this is our parent compound. We are treating it with LDA. So LDA will abstract proton, this alpha proton. We will get an anion here. Then it will rearrange and we will get a lithium enolate like this. Clear? LDA will lead to formation of a lithium enolate like this. It will abstract alpha proton from this side. It will rearrange and it will form a lithium enolate like this. Then it upon this electron density from this oxygen will fall back. Then this carbon carbon double bond will go and attack on this position. So what is the reason why it is attacking on this position and not this position? Any idea? There this is also alkyl halide.
Iodine is better.
What?
Sorry, madam. Sorry. Iodine is a better living group.
Yeah, that is the right answer.
I minus.
Iodine is a better living group, so that is the reason why it is attacking at this position and not this position. Compared to chlorine, iodine is a better living group, so it will attack at this position and iodine will leave and we will get this product. This is the alpha alkylation product we are getting in this reaction. Is the mechanism clear? First, LDA will generate a lithium enolate like this, and then it will undergo alpha alkylation. This oxygen electron will fall down. Then this carbon carbon bond will break and it will attack on this position, and iodine will leave because iodine is a better living group compared to chlorine, and we will get this alpha alkylation product. Is the mechanism clear?
Yes, ma'am.
Yes, ma'am, it's clear.
Okay. So,
Madam, one doubt.
yeah,
One doubt.
yeah.
That LDA
Hmm.
LDA cannot attack ethyl group CH2 proton. It cannot abstract CH2 proton. O ethoxy.
Oh,
O ethyl
ethoxy.
CH2 proton.
It will not be that stabilized then, right?
Oh. Stability will be the issue.
Yeah, yeah. Here it will
Thank you,
be
madam. Thank you.
resonance stabilized, and that is the reason why it is subtracting this proton.
Thank you, madam. Thank you.
Okay. So, out of this four option, the right option will be this, as we have seen in the mechanism. I hope it is clear for everyone why this is the major product. First, lithium enolate will form, and then it will attack at this position because iodine is a better leaving group, and we will get this as the alpha alkylation product. This is clear, right? Any doubt?
No, ma'am.
Okay. We will move to question number 7. So here the major product formed in the following reaction is, here they have given a diketone species and treating it with KOH methanol condition. Out of this four, one major product will be formed. So what is that? So we know that, see here, there are many possibilities for formation of phenolate. Here there is alpha hydrogen at this carbon and at this carbon. Here there is no alpha hydrogen as it is substituted by two methyl groups. So three possibilities are there for formation of enolate. Here KOH can abstract proton from this to generate an enolate here, or it can abstract proton from here to generate an enolate here, or it can abstract a proton from here to generate an enolate here. But out of these three, if enolate is forming in this carbon, then once it is going to attack on this carbonyl, what is the number of atoms involved in that ring? So it will be 1, 2, 3, 4, 5, 6, 7, 8. So an 8-membered ring will be formed. So formation of 8-membered ring is not that favored. And here also we can see when an enolate is generated here, it will lead to formation of, if enolate is generated here, it will attack on this carbonyl, and the size of the ring that will be formed is 1, 2, 3, 4, 5, 6, 7, 8. An 8-membered ring will be formed. So here also the size of the ring is big and it is not that favored. Then we will see what is the possibility, or what is the ring size that is formed when enolate is formed in this side. When alpha proton is abstracted from this side and enolate is formed here, what will be the ring size? So we can see that here this carbon will attack on the carbonyl, and the ring size will be 1, 2, 3, 4, 5, 6. Here a 6-membered ring is formed. So compared to formation of an 8-membered ring, the formation of the 6-membered ring is more favored. So the 6-membered ring will be formed as the major product here. We will see the mechanism for that. I hope why these two other chances are ruled out. Why formation of enolate on this carbon and this carbon is ruled out, because it will lead to formation of 8-membered ring, and when enolate is forming on this carbon, it will result in formation of 6-membered ring after condensation. So that is the reason why the other two possibilities are ruled out. Now we will see the mechanism for this reaction. So, upon treating with KOH, it will lead to formation of an enolate at this position. Other two positions were also possible, like this side and this side also possible, but it will lead to formation of 8-membered ring. Formation of an 8-membered ring is less favored compared to that of a six-membered ring. Six-membered ring is more stable compared to eight-membered ring. That is the reason why these two chances are ruled out. So we will get an enolate from this carbon, and once this oxygen is falling back, this carbon carbon double bond will go and attack on this carbonyl, and we will get an aldol product like this. Is this clear?
Yes,
Excuse me,
ma'am.
madam.
Yeah.
It is based on the stability of ring.
Yeah, ring stability. So
Ring
other,
stability.
in other two cases, it is resulting in formation of eight-membered ring. So formation of eight-membered ring is less possible when there is a chance to form a six-membered ring. So six-membered ring is more stable compared to eight-membered ring. So there is a chance for formation of six-membered ring. So why they will choose to form a eight-membered ring? Is it clear, right?
Ma'am,
Huh?
why 8-member ring is unstable than 6-member ring?
That is because of that formation angle and all. Six-membered ring, that torsional angle all will be it will not cause that much destabilization. I will.
Due to size, ma'am.
And that angles all in six-membered ring, angles that will be formed around the carbons, that will be uh, like uh, it will cause stability. I will explain it in right way in the next class. But in case of eight-membered ring, it will cause torsion, angle strain and all, angular strain and all in the ring, and because of that reason it is unstable. Angular
Okay,
strain will
ma'am.
be there in case of eight-membered ring.
Okay, ma'am. Thank you, ma'am.
I will explain it properly in next class, okay?
Okay, ma'am.
So now we have got the aldol product, and again KOH will be present in the system, and here again alpha hydrogen will be there. Then there is chance for formation of enolate again, and we will get an enolate like this. Then once this enolate is falling back, this double bond will shift to this position, and this hydroxyl group will be eliminated. So we will get this condensation product. Here aldol reaction will take place, and again there is alpha hydrogen. So it will generate an enolate again, and once the enolate is falling back, this double bond will shift here, and this hydroxyl group will be eliminated, resulting in the formation of this aldol condensation product. Is this clear? Here even CB mechanism is taking place. Again, a conjugate base will be formed that is stable. Then it will undergo rearrangement, and elimination is taking place. Clear?
Yes, ma'am.
Okay. So out of this four, which will be the right answer? So as we have seen in the mechanism, this is the right answer. Here you should keep in mind that here this proton will be abstracted by the base, and it will result in formation of a six-membered ring, because formation of eight-membered ring is less favored compared to formation of a six-membered ring. Six-membered ring, five-membered ring, etc. will be stable ring system compared to other ring systems. I hope this is clear for everyone. Here aldol condensation reaction is taking place, intramolecular aldol condensation reaction, because it is taking place within the same system. Can we move on to question number 8? Is question 7 clear for everyone? Any doubts?
Madam, second step, please explain second step.
Okay. Here,
Aldol condensation.
okay. Here, this species is again having one alpha hydrogen here, right? This is the ketone. Adjacent to it, again one alpha hydrogen is there. So, a base is there in the system. That base can abstract this alpha hydrogen. Again, enolate will form. Enolate will form as the base will be abstracting this alpha hydrogen. So, this enolate will be forming, and that enolate it will fall back. Then this double bond will shift in this fashion, and this hydroxyl group will be eliminated. So, we will get this condensation product. Clear?
Thank you, madam. Thank you.
Okay. So this is the right answer for question number 7. And here it is intramolecular aldol condensation reaction taking place. Now we will move on to question 8. So this is question number 8 and they are asked to predict the major product of the following reaction. So as we can see, this is also Reformatsky reaction and we have seen 2 examples today only. So what will be happening here? So first, this bromide species, like in the presence of zinc, the zinc will add on to this bromide species and it will generate this ZnBr compound. Similar to Grignard, it will form this uh, species. Instead of NgBr, we will get ZnBr. Now what will happen? That here it will be having partial negative charge. So this carbon will add on to this aldehyde that we have in the question and it will go and abstract this ZnBr. So we will get this species. Okay, here this partial negative charge on this carbon, it will go and attack on this electrophilic aldehyde center. Then this electron density will shift and O minus will be generated. So here there will be Zn plus. So that O minus will abstract that Zn plus species. So we will get this intermediate and upon doing workup here water will this ZnBr will be removed and we will get hydroxyl group. Sorry, this is OH. OH. Is this clear? This is Reformatsky reaction only. First, this ZnBr species will form, then it will add on to that aldehyde, which is electrophilic, and we will get this intermediate. And then it will undergo hydrolysis, and it will remove the ZnBr species, and we will get hydroxyl. Is this clear mechanism? Hello?
Yes, madam. Yes, madam. Clear.
Okay.
Clear.
Okay, okay.
Thank you. Thank you.
Okay. So we will get the species. So out of this 3, this will be the right answer. So the correct answer is first option A. Now we will move on to question number 9. So here consider the following reaction. They have given a substituted cyclohexanone. Treating with LDA, it will generate one species, lithium enolate species, and then they are treating with acetaldehyde and heating. So what will be the major product that is forming? And they have given 4 options. So we have to see what is the major product forming in this reaction. So we have cyclohexanone, substituted cyclohexanone, and LDA. We know LDA is a bulky base. It is lithium diisopropyl amine. Lithium diisopropyl amine. So it is a bulky base. So here also alpha hydrogen is there. Here also alpha hydrogen is there. But since LDA is a bulky base, it will abstract proton from this side only. Here methyl will cause steric hindrance for LDA. So it will abstract proton from this side, and this bond will, like here a double bond will be forming, and this carbon oxygen double bond will break, and here there will be O minus. Since this LDA is abstracting the proton here, it will lead to formation of lithium diisopropyl amine, and this Li plus will like neutralize this O minus. So we will get OLI species here. This is called a lithium enolate. So here this cyclohexanone will form this lithium enolate species and not on the other side. That is clear, right? That is because of the bulkiness factor of LDA. LDA is a bulky base, so it will lead to formation of this enolate, less substituted enolate. Now what will happen? One second, I will rep this. Now what is happening here? We have this lithium enolate. Then this electron density from oxygen will fall, and this carbon-carbon double bond will attack on the aldehyde. We have given acetaldehyde in the question, so it will attack on this acetaldehyde, and it will lead to formation of this aldol product. And it upon heating, it will undergo condensation as we have seen previously, and it will lead to formation of this product. Like here again enolate will form, it will fall back, and this double bond will shift here, and this hydroxyl group will eliminate, and we will get this condensation product. First lithium enolate will generate, then it will add on to this aldehyde. It will lead to formation of this aldol product, and upon heating, again it will form enolate and it will fall back, and this hydroxyl group will be removed once a double bond is formed here. Clear?
Madam, excuse me, where the second step here, the OH group enolate?
Like I think it is because of LDA is a this reaction or enolate formation is taking place at low temperature. So this aldol product will be formed at a low temperature, and for elimination to take place we should give heat. That is why we are heating, and it will result in the formation of this condensation product. Here again LDA will be a base will be there in the system. Here there is alpha proton, enolate will generate when base will abstract that. Then once it is falling back, this group will be eliminated, this hydroxyl group will be eliminated once it is falling back. This double bond will shift here, and this hydroxyl will eliminate, as we have seen in the previous question.
Or there is a chance of methyl hydrogen also possible, madam?
This
LDA
side,
will abstract
this side.
this side, methyl group hydrogens.
No, alpha hydrogen only it will abstract. Here see, this is the carbonyl group, and the hydrogen that will be alpha, like next to the carbon will be abstracted. So here why LDA is not abstracting this proton, because here methyl group is there. So since LDA is bulky base, that methyl will cause steric hindrance for this LDA to approach to abstract this proton. So that is the reason why here proton is not abstracted. Clear? Any doubt? Hello. Otherwise, on heating, this OH group can remove and a see a carbocation can form here, and this can eliminate to give this product. That is also possible. If LDA is not able to abstract this proton present at this position, there is chance that upon heating, this hydroxyl group will be removed, a carbocation will be generated, and for stabilizing that carbocation, this proton will be removed. That is also a possibility. It can be right. Hello. Like upon heating, see, upon heating, this hydroxyl group can remove, a carbocation will be generated here. Then this proton will be removed so as to neutralize this carbocation, and we will get the species. Is it clear now? Hello? Hello?
Madam, while heating, the OH will leave and it will give carbocation.
Yeah. I think this will
Okay.
be the right way, because LDA, since it is bulky, it have less chance for abstracting this proton again.
Okay, ma'am. Okay, ma'am.
Yes.
Thank you. Thank you, madam. Thank you.
Welcome. So, out of this four options, the right option will be option A. I hope the mechanism is clear for everyone. Now, we will move on to question number 10. What is the major product formed in the given reaction? So, they have given a ketone condensed with this benzene ring and treated with concentrated NaOH. So, in this system, there is alpha hydrogen present on this side only. So, what will happen in this reaction? So, in the presence of NaOH, here this enolate will generate. NaOH will abstract the proton from this side, and it will shift in this fashion. So, we will get this enolate. Now, what is the possibility? Again, in the system, there will be ketone present. This ketone will be present in the system again. So, when the enolate is falling back, it can go and attack on that ketone like this. When the enolate is falling back, it can go and attack on this ketone. This carbon oxygen double bond will break, and we will get O minus like OH. So we will get this species aldol product. We will get this intermolecular aldol product, self condensation product. Like if same species are reacting and we are getting aldol condensation product, it is called a self condensation product. Now again, as we have seen here, there will be proton. Again, enolate will generate, and again elimination will take place, and we will get this condensation product. Here there will be proton. NaOH can abstract that proton. Enolate will generate, and once the enolate is falling back, there is chance for E1CB mechanism to take place, and we will get this product. This is the aldol condensation product from this ketone. Is the mechanism clear? Any doubt?
It is called E1CV mechanism,
Yeah,
madam.
E1CB. Here a conjugate base will be formed which is stabilized, and once it is falling back, this hydroxyl is removed. That is why it is called a E1CB. So first aldol reaction will take place, and then since concentrated NaOH is present, it can undergo again like formation of enolate and then E1CB reaction to get this aldol condensation product. I hope this is clear for everyone. Is this clear?
Yes, ma'am.
Okay. So out of this four options, the right option will be option A. Option A and option D are also similar kind, right? Here, this is also similar only. When this is rearranged and written, it will be similar to this. So the right option will be this one. First enolate will be generated here, then it will again add on to this ketone. That enolate will add on to this ketone. That is, it will undergo self-aldol condensation reaction, self-aldol reaction, and then again it will undergo formation of enolate and then E1CB to get a double bond. That is alpha beta unsaturated ketone. So this is the right answer. I think this is also same only. See, if we just invert this and write, it will be D. So this question is having some problem. So this is the right answer. Clear? Question 10 is clear for everyone?
Yes, madam. Yes, madam.
Okay. Now coming to question number 11. Here they have given a ketone and treating with LDA. They have given that a compound X will be formed, and that compound X they treated with another ketone, and they are telling a compound Y will be formed. So they are asking what is X and what is Y. So in presence of LDA, here there is no alpha hydrogen. This hydrogen will not be abstracted. Here this sp3 hydrogen will be abstracted by LDA. So LDA will abstract the proton from this carbon and an enolate will be generated. So that will be compound X. Formation of lithium enolate will be this first step, and compound X will be the lithium enolate. So out of this 4, like they have given, X is this and X is this. Like here formation of lithium enolate will not be feasible. So the formation of lithium enolate will take place from this side and we will get compound X as this. This is the lithium enolate that will be formed. Now that lithium enolate will add on to this ketone. So we can see this is the lithium enolate we are having. O minus and double bond. Here O minus will be neutralized by this Li plus from LDA. Once it is falling back, this is the ketone we are having. Double bond O. So this enolate will fall back. This carbon-carbon double bond will go and attack on this ketone. And we will get O minus. So what will be the aldol product we are getting here? It will be double bond O, CH2. This will be carbon. Here it will be 1, 2, 3. Here 4 and 5. So this will be 1, 2, 3, and a bond will be formed between carbon 3 and carbon 4, and there will be O minus here, and there will be a medial group here on carbon. This is carbon number 5, sorry, this is atom 5, and there is a medial group here, and there is this R group, which is the cyclohexene. So this can abstract proton from the system and it will generate an aldol product. So out of this four options. The right option for compound Y is this one. It will form this aldol product. So X will be the lithium enolate as we have seen here. LDA will abstract the proton from this less hindered side and we will get this lithium enolate. Then that lithium enolate will add on to this ketone and it will result in the formation of this aldol product. Is it clear why this is the answer? This will be X, which is the lithium enolate, and Y will be aldol product. Is the mechanism clear?
Yes, ma'am.
Okay, so this was the last question in this assignment we will be discussing today. So, if you are having any doubt regarding any of the questions that we have discussed today or any of the previous lectures, you can feel free to ask me.
Excuse me, madam. The
Yeah.
first question we discussed today,
Okay. I will show.
please discuss again.
Okay, I will show. So the first question we have discussed today is we are having a alpha bromo ester and we are treating with zinc and we will get a compound A. Then that compound A we are treating with benzaldehyde and we then with water. Then we will get compound B. So they are asking out of these four options what will be the right option. First they have given compound A is a lithium enolate and then they have mentioned the second step is a benzylic acid rearrangement, that is this will be a benzylic acid rearrangement. Then compound B has two aromatic rings and compound A has two aromatic rings. So here we are having a alpha halo ester and zinc. So we are clear that this is Reformatsky reaction taking place here. So, what is a Reformatsky reaction? So, Reformatsky reaction is an organic reaction where aldehyde or a ketone will condense with alpha haloesters in the presence of metallic zinc to form beta hydroxy ester. So, we will see the mechanism for Reformatsky reaction. So, first the zinc will add on to this oxygen, then this carbon oxygen double bond will break and this electron density will shift leading to formation of a double bond here. Hello. And this bromide will be eliminated, so we will get a zinc enolate here. Now we are having this zinc enolate and an aldehyde. Then it will form a transition state like this and it will undergo a like a condensation reaction like this. Here this oxygen zinc bond will break and a carbon oxygen double bond will be forming. Then this carbon carbon bond it will go and attack on this aldehyde and OZN bond will be formed. So we will get an intermediate like this and it upon workup it will lead to formation of beta hydroxy ester. Beta hydroxy ester meaning here this is alpha position and this is beta position with respect to this ester group. So a beta hydroxy ester will be formed. And coming to the mechanism of the reaction that is given in our question. So we are having this alpha bromo ester. So it upon treatment with zinc, the zinc will add on to this oxygen. This bond will break. This carbon oxygen double bond will break. This electron density will shift here, and this bromide will eliminate, and we will get this species. So this is compound A. So in our question, they have given that A is a lithium enolate. So here A is a zinc enolate. So that option can be ruled out. And they have given that compound A has two aromatic rings. Here only one aromatic ring is present in compound A, that is one phenyl ring. So that option can also be ruled out. Compound A is a zinc enolate and it is having only one phenyl ring, that is one aromatic ring. So the options that were given like compound A is a lithium enolate and compound A has two aromatic rings, that option can be ruled out. Now it will add on to this benzaldehyde. Here we are having a zinc enolate and when upon treatment with this benzaldehyde it will undergo reaction similar to aldol condensation reaction. Uh, f- through this transition state, and we will get this product. And this upon treatment like a workup or hydrolysis, we will get this beta hydroxy ester. So compound B, here we can see that compound B is having two aromatic rings, so that will be the right option. And they have given that the second step is benzylic acid rearrangement. Here no benzylic acid rearrangement is taking place. Here condensation reaction that is similar to aldol is taking place with the presence of zinc enolate. So the correct option will be compound B is having two aromatic rings, as we can see here, two phenyl groups, that is two aromatic rings. So is it clear? Compound A is zinc enolate, so this can be ruled out. Second step is similar to aldol condensation. It is not a benzylic acid rearrangement. Then compound A has only one aromatic ring, so it can also be ruled out. So the correct option will be compound B has two aromatic rings. Is this clear?
Yes, madam. Yes, madam. Thank you, madam. Thank you.
Welcome. So if anyone have any other doubts, if no doubts, we can wind up this session, and we can meet next week for solving week 7 assignments.
Ma'am, these assignments will be available, this problem solving will be available in the website?
Problem solving, yeah, they are uploading in the website as well as we are uploading in YouTube channel. That link I can share you. I will show.
Sure, ma'am.
Okay.
Previous last week, madam, last week.
Every last 5 weeks assignments are sold, and that YouTube channel I can show you. 1 second. So this is my channel, PMRF NPTL TA Anisha Suresh. So you can go to this channel, and all the questions that we have, like all the assignments we have discussed previously, are available here. Starting from week 0 to week 5, I have uploaded, and whatever lecture we have done today, that will also be uploaded soon. Is this clear?
Thank you, madam.
Okay.
Yes, ma'am. Thank you, madam. Thank you.
Okay,
Thank you.
welcome. So we can wind up today's session. Thank you for joining.
Thank you, madam. Thank you.
Welcome.